everybody. I hope everyone's having a wonderful day. So we're going to talk a little bit about Big O, and then we're going to be talking more about analysis of algorithms. So let's talk about some properties of Big O. So I'm going to summarize these for you. So the great thing is that all of these technically can be proven using the definitions that we've been using so far. But here's the idea. I'm going to imagine I have three complexity functions, f, g, and h. So the first property that I have in my list is the so-called transitivity property. So Big O is transitive. That means that if I say that if f is Big O of g and g is Big O of h, what does that mean? It means that f is Big O of h. That means it kind of cuts out the middle person here, so it should go right to f all the way to h. So that's how the transitive property here works. So Big O has this property. So for example, if I give you some function that's linear, and then I give you an intermediate one that's, say, quadratic, and h is cubic, then I can say, of course, n is Big O of n cubed, right? So next, number two. So if I just give you some positive real constant, then if I know that f is Big O of g, then that constant times the original function f that was Big O of g is also Big O of g when I multiply it by c. The third one here is that if I know that two functions are both Big O of h, then their sum is also Big O of h. The last one, if you know some calculus or limits, you'll notice that this should look awfully familiar to you if you're interested in the formal definition of a limit. That's why the definition of Big O looks awfully familiar if you know the formal definition of a limit. It's because of this. So the limit theorem here, if you know that the limit as n approaches infinity of f of n over g of n is not equal to infinity, then you could say that f is Big O of g. In fact, if it's exactly equal to 0, the limit, then you can say that f is Big O of g strictly. There are some other asymptotic notations I'm not going to talk about in this course, but if you take 355, I'll talk a bit more about those towards the beginning of that class. So I'll talk about some other asymptotic notations, which are ones like so-called Big Omega, and then there's another one called Big Theta. There's other ones as well, like little o. But we're just going to care about Big O here in this course. So I'm going to prove the third property here. Let's actually write out the proof for this. Now, remember, like usual, I have to tell you how I'm going to do it. So we will prove the claim using the definition of Big O. I'm just going to use the definition of Big O. You're going to see that all I'm really going to do is pull out the bits and pieces that I know. So remember, it's if this and that, then this has to follow from that. So I have this as a given and this as a given as true. So both of these are true under my assumptions here. And all I have to do is now, given those two things, is it also that this is true? So I'm just going to use the definition. So this is the game plan here. I'm just going to use the definition on this statement, and I'm going to use the definition on that statement, because both of these have to be, there are premises here. So our hypotheses. Okay, since f of n is Big O of h of n, what does that mean? You just use the definition. There exists c sub 1, which is a positive real constant, and n sub 1, which is a positive integer constant. Notice I've used subscripts here. Makes it a little easier, but I'm going to use this twice, so I'm going to try to massage it into another invocation of the definition later. You'll see why I kind of pick it this way. Just make things read very easily. So we have, there exists these two such that for all n greater or equal to n sub 1, that f of n is less than or equal to c sub 1 times h of n. We have that. So that's me just invoking that. Also, g of n is, we'll go with is big O of h of n. So there exists constants c sub 2 or c2, which is a positive real constant, right? And n sub 2, which is a positive integer, such that what? It's that g of n is less than or equal to c2 times h of n, right? And that's for all n greater or equal to n2 here. So remember, all I've done is I've just said what the definition means for f is big O of h and g is big O of h, right? That's all I've done. So now I'm just going to take the bits and pieces that I have here and try to string them together so I can derive a c and an n0 like I did before. Remember the original game plan when I showed something is big O of another thing? My goal was to find a c and an n0. I'm just going to do that same strategy here. Now I have a bunch of constants kicking around. I'm going to use them to string together one kind of super constant for each one of them. Now let n0 equal to the max of n1 and n2. So I'm going to pick n0 to be the maximum of n sub 1 and n sub 2. If I pick the larger of these two, I'm okay, right? So remember, I just need to make sure this n0 is big enough, so it's going to kind of capture both of these two statements. Then, now watch this, this is where it gets fun. Then, f of n plus g of n, I'm just going to combine these two by adding the two inequalities that I have here, which is less than or equal to c1 times h of n plus c2 times h of n. So I have these. So all I've done is just added those two inequalities together, which, of course, that is equal to c1 plus c2 all multiplied by h of n. And we know this, which holds for all n greater or equal to n0. We know this holds because I've selected n0 to be bigger, the larger of these two numbers. So now I have this to play around with. So what should I pick as c then? What's the constant c going to look like? Maybe combine these two together and there's our new c. So I'm going to choose c is equal to c1 plus c2. Then f of n plus g of n is less than or equal to c times h of n for all n greater or equal to n0 as desired. Remember, that's the definition of big O, right? Remember, I said that I was going to prove this using the definition of big O, as desired. Therefore, I'm running out of space here. My therefore is getting shrunk and contracted into the corner of the board here. Therefore, property 3 holds. And I've done my proof. I'm going to indicate that I'm end of the proof. And I've thus proved the claim. See, it's nothing too scary. All I do, remember, it's not too bad. All I do is I just invoke the definition of big O for each one of these, And what I do is I cleverly stick them together so I can invoke the definition of big O for my larger consequence. So this is the thing I'm trying to actually prove given these two facts, okay? So now what we're going to do is I'm going to switch gears and talk about analysis. I'm going to actually start analyzing algorithms with our understanding of big O, okay? So let's consider an iterative example. So this is going to be a new topic heading. Okay, an iterative example. So what we're going to do is we're going to consider the sorting problem again. So I'm going to pick one sorting algorithm and I'm going to perform worst case analysis on the sorting algorithm. I'm just going to pick one that you probably are familiar with. So I'm going to consider the sorting problem. An algorithm that solves this problem is insertion sort. So I'm going to use insertion sort here. Remember, insertion sort here is given an array of size n, which is my input. The output is A sorted in non-decreasing order. So what we're going to do is we're going to consider elements A sub 1, A sub 2, A sub 3, all the way up to A sub n minus 1. So I'm going to have my for loop where I start the initial value at 1 and I go up until and including n minus 1. So I go for I is assigned 1 to n minus 1. I'm going to do the following. So this is just a for loop here. And I just give you the lower and upper bound. Remember, the upper bound is inclusive here. So what I do is I assign x to be the value at a sub whatever position of I. Then I go just simply assign j to be the index just before it. And what I do is I perform a little shuffle. So if the key that I have in here is less than the one that I'm considering, I shuffle that element to the right, and then I might potentially have to shuffle more elements over to the right until I find the position to put my current element that I'm considering. So this isn't too terribly complicated. The big thing here is I have a while loop. Just for sake, I put a comment here just saying the end of the while loop, and I have an end for the for loop. All I just do is I just keep doing this until I reach where j is potentially equal to 0, or I find the place for which I insert my element, okay? So I think of it like a little sliding puzzle. I'm just moving each one of the elements over until I find the spot where it's sorted from left to right up to that position in my loop. Okay? So I just find this position, and then I just insert it in. Hence the name insertion sort. Then when I'm done my for loop, I return the array, and we're done. Okay? That's not too terribly bad. So what we're going to do is I'm going to perform an analysis on this algorithm. So I'm going to use the same strategy I used last time, but you're going to notice I'm going to be a lot less picky about going through all the lines. I'm going to help you try to identify the lines that are going to occur more often than any other line. So before we get into looking at these lines, we're going to consider the worst case scenario. So I want you to think about what's the worst case scenario for insertion sort. Because we're going to be doing worst case analysis, so I need to identify those worst instances. So remember, I want to maximize the number of iterations that occur in this while loop. Because remember, it's still, no matter what instance I give you, it's going to go through this n minus, it's going to go n minus, let's see. We'll calculate it out after, okay? I don't want to give you all the answers yet. So how many times is this going to occur? It's going to happen regardless, depending on n. This part is the part we want to target here. We want to maximize the number of times this while loop occurs. So how do we do that? Well, think about it. I have each one of my elements. Now imagine if I gave you the elements in reverse sorted order. So from biggest to smallest. So if I go through this every single time, you'll notice that I have to perform that insertion, but I have to slide all of the elements that I've considered up to this point 1 over so I can insert it in its appropriate location. But I have to do that until I get all the way down to where it should be sorted, okay? So that's going to be our worst case scenario. So I'm just going to mention that we want to maximize the number of iterations in the innermost loop. Right? That's the while loop. Because this is the nested loop here. Observe that this is when A is in reverse sorted order. So it's reverse sorted order. So you'll notice that every single time I just kind of shift all the elements all the way until I find the position for which it sorts all the elements up to that point. So we're going to consider instances that look like that. So now let's calculate the time complexity. Now I don't need to convince you of the correctness of insertion sort, so I'm just going to skip that. Instead I'm going to calculate its worst case time complexity. Now, I want you to look at these lines here. Okay, when I calculated out using an exact analysis where I counted out all the number of times each one of these lines occurs, each one of them occurring with a simple number of operations at some constant number. So when I did this, I noticed that if I count certain ones, they happen a certain number of times with respect to the input. So what you want to do is you want to target the lines that occur more often than any other line in the execution of the algorithm in the worst case. So is it this for loop? Well, this for loop occurs how many times? Okay, 1, 2, 3, 4, 5, all the way up to n-1. Is that the most? No, right? How about this one? Well, that happens for each one of these iterations, so no. How about this one? Now, it's going to still happen at least those n-1 times. Okay, how about down here? Okay, that's just going to happen once per iteration of this for loop. This happens only once, right? That's not a good candidate for a line that's going to occur more often than any other line. It's this while loop here. Look at this. So every single time this occurs, this iteration occurs. But how many times does this happen? We're going to calculate that out. But lines 4 through 6 are the ones you'd want to identify in your worst case analysis. So notice that these lines occur more often than any other line in the algorithm in the worst case. So I'm going to convince you that just selecting one of these three lines will be sufficient for our worst case analysis. I don't have to count every single one of them. So my goal is just to convince you of this. So I want you to observe that in the worst case, no line occurs more than lines 4 through 6. And, now this is important as well, and every other line takes constant time to be evaluated. Now, you might ask, Dan, why are you saying that? What I'm saying is each one of these, when I evaluate that line, this is considered a simple operation. When I encounter this line, simple operation, simple operation. However, the for loop can happen many times, like because it goes over and over again, but each one of these takes constant time to evaluate, right? In itself. The reason why I have to say this is because I might potentially have one of these being a more complicated operation, like a subroutine. So some method that gets called might not be a simple operation, so I have to account for these. I can't just simply ignore, like if there's some method that happens that isn't a simple operation, I can't ignore it. I have to account for it too. So I'm just saying that we don't have to worry about those because each one of these, those specific lines, when they occur once, takes constant time. We will count the number of times line 5 occurs. Since this line takes constant time, we will treat it as a single step. Okay, so I've just selected line 5. You could do this analysis with line 4, line 5, or line 6. I'm going to pick line 5 just because I feel like it. If you did this analysis with any of these 3 lines, you'd still get the same result at the end in terms of asymptotics. Now, the most important thing also to mention here, now, as the course progresses, you may not have to mention this every single time, but since the line takes constant time, we'll treat it like a single step. Now, why can we do this? Well, if it takes constant time, remember, that's big O of 1, right? That's constant time. So, remember, by your intuition with big O, if it's a constant time, it's independent of the input size, so I may as well just treat it like one step. Okay? So, whenever I see constant, I can treat it like a single step. That's the cool part about the RAM model when we think about it this way. Okay? So that's what I mean by treating it like a single step. Okay, I've got the board erased. Let's continue. So notice that the outermost loop performs n minus 1 minus 1 plus 1, which equals n minus 1 iterations. So, remember I said that the upper limit is n minus 1, which it occurs on that iteration. And it goes from 1 up to that. This is the upper limit. This is the lower limit. They all occur, but I want to count them. A very common counting rule you can use is the upper limit minus the lower limit. So upper limit was U, the lower limit was L. If you ever want to count how many times this occurs, it's U minus L plus 1. U would be n minus 1, L would be 1. So if I ever want to count how many times something occurs in terms of a number of discrete objects, this would be sufficient. So this gives me n minus 1. This should be pretty straightforward because you notice it's 1, 2, 3, 4, 5. How many times does this happen? N minus 1 times, right? However, the reason why I bring up this counting rule is that if this was 0, it would not be n minus 1. It would be n, right? So if you just put in 0 here, you'll notice you just get n. Okay. For value I, so I'm going to consider a particular value of I now, because remember, this is a nested loop. So I'm going to imagine I'm given I, and I'm going to consider the rest inside here. For value I, the innermost loop, which, remember, this is line 4, occurs how many times? Okay, well, let's think about it. It's I minus 1. Remember, it starts off, j is set to I minus 1. And when I'm doing this every single time, when it's in reverse sorted order, I have to shuffle all of the elements over until I reach position 0. So they all get slid over, and then I insert into the very first position. So that means I'm going to have to go from I minus 1 until this condition gets violated, right? So that means I'm going to have to go all the way down to when j is in fact 0. So when j is 0, I'm going to use my little counting trick again. I minus 1 minus 0 plus 1 is just I. This shouldn't be too hard to see. So I slide all the way down until I reach the point where a sub 0 is greater than this. And then you'll see, okay, well, I've slid them all over, but now, look, it's invalidated, so I know this is where I'm going to stick it. So all I'm doing is I'm counting up how many times this line is going to occur. Remember, if I counted line form, I would have one extra iteration to verify the condition is still satisfied or not. That's why I select the one inside the loop. It typically makes things a little easier to calculate. This is because, so I'm just going to explain what I just said in words. This is because j is set to I minus 1, and the while loop continues when j is greater than or equal to 0. Thus, the number of times line 5 occurs is at most the following. Now remember, the outer loop occurs how many times again? N minus 1 times. The innermost loop for a given value of I. Now remember, I starts at 1, it goes up to n minus 1. I want you to visualize this like a summation. I'm trying to add all the number of steps. So it starts off at I is 1, it goes up to n minus 1. How many steps of work do I do here? I already told you that at this particular line, it occurs I times at most. So what does it look like? It occurs at most the sum from I is equal to 1 to n minus 1. So from I is equal to 1 to n minus 1. How many times does it occur? I times, which the great thing is that we already know what that is. That is the arithmetic series, right? So this is just n times what? Now I have to be a bit careful here. So is it really n times n minus 1? You have to be careful because remember the upper limit is n minus 1 here. Okay, the upper limit is n minus 1. Remember that the original one for the closed form is n. So I'm going to have to write n minus 1 times n minus 2. N times n minus 1. What am I saying? It's n minus 1 times n. Silly, Dan. See, I do these things just so you're keeping your eyes on me here. So I have n minus 1, so that's what n is, right? The original n value of our closed form is n times n plus 1 over 2. This is what n is now, so that's n minus 1 times n over 2. That's what the closed form pops out. Thus, line 5 is executed n times n minus 1 over 2 times, no comma, let's not have the comma there. In the worst case, what is that? This is big O of n squared. And we're done. You should know that insertion sort takes quadratic time. I've just derived it here for you. So if you picked line 6, the analysis would be exactly the same as this because I'm using the same observations. If I pick line 4, it should still spit out a quadratic for you anyways, but it won't be the exact same one. Okay, so this is how we can analyze insertion sort. So that's our worst case analysis, and I've just brought it together with the big O. So what we're going to do now is I'm going to consider another algorithm. We're going to go back to another problem that we looked at. So we're going to go back to our easy search problem. Now remember, I had a search problem where I made some particular assumptions that made things a little easier. Remember, I said I was going to come back to it, and this is now that time. Back to our easy search problem. Okay, so I want to remember, so we're going to say recall. Recall that we are given, and we are given an array L with n integers and the value x, which we call the key very often, where L is sorted in non-decreasing order. Determine if x is in L. We're going to give its location if it exists. So that's our problem, remember? Remember we talked about this. So, remember earlier I gave you linear search. And we saw that linear search is linear in the input size. So it's a linear time algorithm. You can show that that is big O of n, as I mentioned the other day. So we showed that linear search, which I'll abbreviate as LS, solves this problem in big O of n time in the worst case. In the worst case. Now, I should mention for you, if L is unsorted, I mentioned this actually the other day, but I feel like writing it down anyways. If L is unsorted, linear search is ideal to use. There is no algorithm with running time less than linear search. So when the array is unsorted, linear search is actually an optimal algorithm. That means that you cannot do better than linear search in the worst case. It actually matches a so-called lower bound on the search problem. When I give you an array, if it's unsorted, linear search is actually going to match the theoretical lower bound possible for searching like this. Why can you say that? Well, I'll give you a very basic sketch of the idea. So I give you an array L, and I'm going to ask you a question. If I plucked off some location from the array, and I wanted to know if I pluck off a location and I say, okay, is it in this location? The answer is, okay, well, I need to check it, but I also have to check every other element, right? So if I don't find it in that location, I have to check other ones, right? Well, that means I have to check each one of those positions. I have to touch at least one of the elements to check it. But I have to do it for all of them, right? In the worst case. So I have to touch at least one of the elements in that array to guarantee I can find it. So very similar arguments apply for other things like computing the maximum in an unsorted array. An argument like this very much applies. It's a so-called adversarial argument. So I could just give you some array and I say, hey, look, where is it? Okay, well, I could just keep giving you things where if you tried guessing where the location was, I could just create another instance where it's not in that position. So all I have to do is just simply check and say, hey, look, I have to look at all of them. So that brings me to talking about what we're going to do now. So that's in the case when the array is unsorted. When it is sorted, we can do actually better than this. However, if L is sorted, there is a more efficient algorithm. More efficient algorithm called, and you might know this algorithm, it's called binary search. So if the array is sorted in advance, we can use so-called binary search. So I'm just going to write up binary search on the board here. Give me one moment. I'm going to do some little magic here. Voila! Here we go. So here's binary search. So it's going to be given L, the array, X, which is going to be our value or key. L is going to be a lower bound L, and U is going to be an upper bound. So what we're going to do is, so this is a recursive algorithm. So it means it's going to invoke itself using different sets of parameters until we eventually either reach a point for which we find the key, or we just simply run out of elements to check. So the whole idea in binary search is we're going to check a middle position between a given range, and if the middle position contains the key, we return it. However, if we don't, then we ignore the middle position, and then we kind of consider two halves. Either if the key is less than the position's element, then I consider the left half. So I ignore the right half. Then I recursively apply the problem to this left half. If the key is larger than the element I've considered, then I consider the right half. So this is a recursive method. Now, just as a note, I've written it in a way such that I'm given L and U. In the original problem, we just had L and X. So this is a recursive method that's going to be invoked by an initial method called a driver method. So this will be a recursive method that passes this one 0 as L, so lowercase fancy L, and the upper limit will be n minus 1. So this will be some method that will look something like binary search, LX, and it invokes this one, so it's binary search, LX, 0, n minus 1. So that's what it will do. So that's what I'm calling a driver method. So this is the recursive method that the driver method will use. We're going to analyze this recursive method because the driver method is just going to call this one anyways. And all the work's being done by this. So we have two possibilities. Either we find out that our lower bound crosses with the upper bound, meaning we've checked all the possible positions. If that's the case, we return -1. Otherwise, we have some searching to do. So the reason why we call it binary is we perform this halving procedure. It's either going to be in the left half or the right half, or we found it. So this left halving, right halving, this bisecting, that's where the binary and binary search comes from. So I assign the middle position. So remember, that's the floor right there. So I just round down the result of L plus U divided by 2. So that's our middle position. It might not exactly be in the middle. It might be a little bit off from the middle if we have, say, an even number of positions. Now, if the element in that position is equal to the key, I return that position because I found it. Otherwise, I consider either the right half, so I ignore the middle position. I just consider 1 beyond that and the remainder up to this U position. Or I consider the left half. It's nothing too sophisticated. The big thing is that this is a recursive method. It isn't like the other examples I've shown you so far. So I'm going to do an example just to illustrate this. So I've drawn out this full-blown example. We're going to start up here. So the algorithm begins by setting L to 0, right? So L is 0. U is n minus 1. So the n here would be 10. So it would be indexing the last position in our array. So what we're going to do is we have to compute the middle position. So what's the middle position? It's 0 plus 9 divided by 2, rounded down. What's 9 divided by 2? Well, that's 4.5, right? But I'm going to round down. So mid's going to be located right here. So what I'm going to do in my example is I'm going to look for, what am I going to look for? I guess I should get a little ahead of myself here. Let's do an example with x is 42. So I'm getting a little ahead of myself. So x is 42 and L is provided over here. Remember, L is sorted. See, I'm getting really excited here. So, anyways, so is 20 equal to 42? Remember, the answer is 42. Everybody knows the answer is 42. No, it isn't, right? Oh, rats. So isn't this? So is 42 greater than the current value I'm looking at? The answer is, of course, yes, right? So what am I going to do? That means I'm going to have to discard. So I'm going to apply a recursive method. So I should mention that when we're doing recursion, we have to keep in mind the idea that we have this so-called call stack that stores activation records. So these are your calls to the function or method. So our initial call for binary search is here with L, 0, and n minus 1 right here. So when I initially call the method, it goes on the call stack like this. So I'll refer to, when I apply the recursive call, I'll call this A here, just to make this easier. So remember, in my algorithm, I then apply recursively binary search to the right half, right? So I'm going to straight up say, hey, look, none of this matters, because we're never going to look at it ever again. Because remember, it's sorted. I already know that 42 is not going to be in any of these. But likewise, do I discard 5? Yeah, I don't discard 5. Don't discard 5. Remember, we haven't looked at that one. We only know that 20 and below are not going to be 42. So now we're going to do the same thing. Well, what's mid? Well, remember, L is now going to be passed as what? Mid plus 1. What's mid plus 1? Well, this right here is L, which is 5. U hasn't changed. So U is 9, L is 5. So what's mid? Mid is 5 plus 9 over 2. So that's 14 divided by 2, which is 7. So mid's right here. So, and by the way, when we're executing this one, A is on the call stack here. We're not quite done yet. So, let's look at that position. Is that 42? No. It's not 42. So what does that mean? Well, we look at our algorithm, so we aren't going to satisfy that condition there. And we know that x is in fact less than our current amount, which is 43. So it means we're going to apply to the left half of my current interval here between L and U. So it means that the next one, now remember, I already discarded this. I'm going to call this B. So B is right here. And notice that now because I already checked 7 and up, we know it's not going to be in any of those. Okay, what's L? L is still 5, right? I haven't changed what L is. So L is right here. What's U? U is 6. It's mid minus 1. So this is U. So we have 5 plus 6, which is 11, divided by 2. How much is that? Well, round it down, it's just 5. So mid is this is mid. I'm kind of running on a space here. So mid is right here. So mid is 22. Is 22 42? No. 42 is bigger. So I know I need to consider the right half. So here we go. So now I can just simply ignore all of these so far. And now notice that L and U are in fact going to be equal to one another in my next call. So I recursively apply it with the array L. And this is now C. C went onto the call stack. And remember, I can't lose these until I'm done properly executing. Because remember, each one of these requires me to finish the computation of this recursive call. So each one of these is my activation record. And now look at this. I have L and U are matched down here. And it's going to actually also be mid as well. So mid is also here. Because 6 plus 6 is 12. Going by 2 is 6. So is 29 42? No, right? So it means, look at this. Okay, I've looked at the entire thing, and I know for a fact at this stage that it's going to assign and say, hey, look, well, it's not equal. Well, it's going to fall into one of these cases over here. And I believe U is going to become 6. U is going to become 6, and L is going to become 7. That's our condition right here, where they overlap. And we're done. So it would return -1 here. And it's worth noting that this is activation record D. So this is our call stack. So here's D. So when I finish executing, when I return -1 here, what happens? What happens, everybody? Okay, when I recall -1, it finishes executing here. So I get -1. So it passes -1 back here as part of its return statement. And what happens? This goes away. It goes caca. It's done. We finished executing that recursive call binary search. This one is depending on the computation of the binary search. For this case, for C, it returns -1 because it got past -1 from its return call from D. So it gets back -1. Okay, how about B? Okay, remember, it returns -1 as well. And it's done. And it returns -1. And it's done. And this one finished, right? Okay, well, it returns -1. And we're done. So it returns -1, and we can conclude that the array it doesn't have 42 in it. It's not the answer. Whoops. So this is an example where I have 10 integers. The key is 42. 42 is not in here. It's not the answer, unfortunately. Okay. So before we get into any of the nitty-gritty, so I want you to remember this call stack here. It's going to take a place, and it's going to be very relevant when we do our space complexity analysis. So what's the worst case scenario? Remember, before we can do our time complexity, we need to determine the worst case. So I want to figure out the worst case scenario. So I'm going to say the maximum of recursive calls occurs when? When does it occur? Occur when x is not in L. It's very similar to how linear search is worst case is. So remember, we have to keep going and splitting in two parts and considering only a half every single time. This worst case scenario is the same one. It's the one for which we have to consider all possible positions, which is every time I take a half minus 1. So we're going to compute the time complexity. I'm going to start the time complexity, and then next class we're going to finish it, okay? So let me just get started. I'm going to start off with how we're going to approach this. Now, this is a recursive algorithm, so we have kind of two pieces we need to always consider. So there is the non-recursive steps that occur within this itself. So we would first analyze the algorithm where we assume that the recursion, like this recursive call, takes constant time. Then what we need to do is we have to consider the recursive calls. And what we'll do is we'll take these non-recursive steps, this non-recursive work, combine it with some sort of thing that captures the recursive calls, so that when we sum these two things together, we get the total running time in the worst case, okay? So that's going to be the idea, and that's generally how you analyze recursive algorithms. So there are two parts to this analysis. The non-recursive steps, and the recursive part. Let us consider the base case, and the recursive case. So remember, recursive algorithms have two parts, a recursive part and a base case. What's the base case? It's right here, right? This is the base case. This is the recursive case where we get our recursive calls, right? So the whole idea is we break the problem down, eventually we get to the base case. It's nothing too sophisticated. So let's count up the lines. So I'm just going to number these again, like I did before. Okay, which lines are of particular interest? We're just going to count them all. But you're going to notice that I'm just going to kind of contract a lot of these into nice, simple analyses. So I'm going to say that right now. So here we go. So line one takes some constant C1 steps to occur. And the non-recursive work in lines 2 through 5 are some constant C2 number of steps. There's some constant number. So if I look at 2 through 5, if I assume that these recursive calls, if I just ignore the recursion each of these, all of these are going to take constant time. So I'm just going to collapse that into just some constant. As C1 and C2 are constants, each is big O of 1. However, the recursive step makes one recursive call, right? There's only one of these can occur. They both can't happen in one execution of this recursive method. Makes one recursive call where the number of elements, U minus L is halved. So when I say halved, I mean not cleanly in the middle, but kind of close. So we will make a simplifying assumption that both halves of the array have the same size. N minus 1 over 2. Now where does n minus 1 over 2 come from? Because notice every time I do this interval, I discard the middle element, then I consider the other half, right? So I'm just making a simplifying assumption so that because remember, every time I discard the other half entirely, so I only need to really look at the part that's actually supposed to be a part of my execution of the algorithm. So this is where this assumption comes from. So it would be otherwise n over 2, but remember, I remove one element. So I'm just going to make this as a simplifying assumption. So if you were to do it more meticulously, you'd still get the same result, but I find this reads a little bit easier in terms of the analysis. So we're going to let T of n be our complexity function. So I'm going to give it a name. It's a little bit more complicated. Be a complexity function. So I'm going to combine the non-recursive work with the recursive work. So remember, now I'm going to just take on, okay, well now these are going to happen if they need to happen. And I have some way of capturing that now, because remember, I now have some idea of how many calls are going to happen. It's while this is not satisfied, right? Goes right to that else. So putting this together, we get the recurrence relation. So this is just a function that's written in terms of itself in the way that we're going to use it. We get the recurrence relation T of n is equal to T of n minus 1 over 2 plus 1 if n is greater than 0 and T of 0 equals 1. So remember, this is representing our recursive case. So this is the recursive calls. This is our non-recursive work. Remember, we established that non-recursive work is all going to take constant time. So remember, when I ignore the recursion, just pretend that these are simple operations, this is going to take big O of 1. So that's where the 1 comes from. This is from our recursion. So when we come back next time, first I want to apologize for taking a little extra time today. When we come back, we're going to analyze this using some neat little technique. So we'll come back to this next time. So thank you very much and have yourself a beautiful day.